In this video we're going to take a look at the Reg challenge on HackTheBox. It's an easy Pwn challenge, and the description says this is a basic buffer overflow exploit, try to get the flag. So I'll start an instance here and let's download the files and try and get this working locally before we try it on the server. So I'm going to copy over this reg file, and let's start by doing some basic file checks. So first of all, we'll just check the file type. We'll see that it's a 64-bit executable. Let's run checksec reg, and this will tell us what protections are enabled. So no execute is enabled, so we're not going to be able to execute code that we place on the stack. We don't have to worry about pi, and there's no stack canaries. So that's fine. Let's do some of our usual checks. Just check the strings. We can see some functions here. We can get an idea of what's happening in the program. It's going to ask us for our name. There's a congratulations somewhere which we might want to search for if we're struggling to find where the flag is printed or loaded or whatever. Cool. Let's chmod reg and let's try to run it and just get an idea what happens when we run it. We'll put in a name, crypto, and we get registered. Let's run that again, ltrace./reg, just so we can see what's actually happening here. It's asking for the name, and if there was some kind of comparison happening here, if it was comparing our username to something else, then we'll be able to see that quite easily. Again, I'll put in crypto, and we can see then it's using the gets call to take crypto, and then it's putting out registered. Since this is a buffer overflow problem, presumably if we put in a really long input here, we'll crash the program. See there we get a segmentation fault. So we need to try and find out how many bytes, how many characters we can enter here before we actually overwrite the instruction pointer, which is causing this segmentation fault. And we also want to find out what else is going on in the program. So we could disassemble it, or we could try and use something like Ghidra to actually decompile it, Ghidra or IDA Pro or something like that, binary ninja, whatever. So just quickly, I'll create a project here. This isn't really necessary, but just why not cover as many things as possible. We'll create a project called reg, and I'll import the file, which is, where is it? It's HackTheBox Pwn reg. And if we double click that, then we can open it up. Just hit yes, do whatever basic analysis checks it wants. And let's go here. Do we have a main function we can go to? Let's check the main function. And we have our main function, so we have our decompiled code on the right, and whatever we click on here, it's going to show us the assembly code on this window on the left. So let's double click on run, which is executing, and we'll see that a variable is declared here, 48 bytes. It's initialize is executed, which we can have a look at here. Let's go back, and then it calls printf asking for our name. It calls gets using this buffer it's set up at the beginning, and then it calls puts. So there's no actual checks here on that gets. If fgets was used, it could be done securely. If we go man gets, you'll see here never use this function, so it shouldn't be used outside of these testing purposes. And we could keep having a look around in here. Another thing we could have done was have a look for, if this was a bigger program, we might want to search for strings, and then go and look in the strings, and we'll see, oh, congratulations and flag. So there's obviously some stuff in here that we're not seeing through the main method. We looked through all of those functions, but there's some function somewhere else which is never actually called. So let's select this, the flag.txt, and let's go here. We have flag.txt. We also have a congratulations. Can we see where this is referenced. Oh, xref. Oops, because I can't see the full screen here. And we'll see here then there's a puts congratulations for this method, this function called winner, and it puts congratulations, it opens flag.txt, and then it will print that out. So whenever we're testing this locally, what we might want to do is create a flag.txt and put a fake flag in it, and then we can just make sure that we get it all working locally before we try this on the server. We can also check for our addresses in here. So we have this winner function. We know now where the address is for the function, but let's go and see if we can find that some other ways as well. In fact, let me close down Ghidra. We'll not return to it. Anything else we need to retrieve, we'll do through something else. So we can use object dump. We can use GDB and the PwnDbg or Jeff or Peda plugins, or we can use Radar or something like that. So we'll refer to other tools like that if we need to. So let's run a couple more tools here. We can do readelf-s and reg and have a look here at the sections, and we have our functions here as well. So we can see that the address of the winner function is right here. If we need that at any point, which we probably will, we could also go open up Radar and do all checks. We can list the functions here, and again quite easily get the address. We can select the winner function if we wanted to, and then disassemble that and have a look at the assembly code. We can see here the congratulations call, and if you do capital V there, you can change this mode from like graph, visual to graph and things like that. Here's the graph view here, or the like flowchart view. So cool, let's open up PwnDbg and see if we can actually find out what the offset is of the instruction pointer. So I'm going to open GDB PwnDbg. I have some other videos where I go through setting this up. You can actually set up, in fact, let me quickly just refer to PwnDbg, Peda, Jeff. You can use this script to set up all three plugins, and then you can just use you can open whichever plugin you choose at the time. Some might have benefits in some ways, and I think Peda and PwnDbg are my favorites. Peda for the pattern search and PwnDbg for everything else, but because it's only really the pattern search I really like in Peda, I mostly just use PwnDbg because I can deal with the lack of searching functionality. Let's open this up anyway. Reg. So we can look at the functions in here as well in PwnDbg. We can do info functions, get a list of these up. See, we have our main, we have the run, and then we have this winner function, which is where we want to try and get to. So essentially this is what's known as a return to win challenge. Our goal is to return to the win function, and so we need to overflow the instruction pointer with the address of this function. Essentially, that's our goal. So we could also disassemble in here as well. We can disassemble, say, the winner function, and if there was somewhere particularly we wanted to get an address of, we can grab the addresses from here. Okay, so let's generate a pattern here. I'm going to do cyclic dash, I'll do cyclic 100, and it'll generate a cyclic pattern here. If there are any characters we want to avoid, we can do that. There's some different, does it give you, yeah, so it's possible to set the alphabet here as well. If you need to avoid bad characters and stuff, it's worth remembering. So we've got a cyclic pattern. Let's copy it. Let's run the program, and it's going to ask us for our name. We'll paste that in, the cyclic pattern, and you'll see we've crashed the program. And what we want to try and identify now is at what point did we overflow this RIP, the instruction pointer. On on 32-bit applications we would actually see some of this pattern in here, but because on 64-bit, if the instruction doesn't make sense, essentially if it's an invalid address, it won't even try to execute it. It won't even put it into the RIP, should I say. So that's fine. It just means we can take the offset from somewhere else. So we can take the offset of the NAAA here, and then whatever comes after that is our RIP, or we can just grab the offset of this and say cyclic -L to lookup, or -O I think you can do as well, and then we paste that in, and we see that we have to write 56 bytes before we're going to overwrite the RSP with our values. So ordinarily I might go through and say, let's do Python 2-C, and then we'll print A times 56 plus B times 6 plus C times, let's say, 50, and copy this. And if we go back and try to run it again and paste that in, it just can sometimes help visualize what's going on. So we can see here that we wrote all these A's. We can have a look. Let's go info stack. So we can see that we wrote all the A's, and then we have a series of B's. Actually, it's probably a better look at it here. We have all these A's that are filling up, and then we have our 6 B's, which are in the 6 B's would go to the RIP. It's just because they don't exist, it's not quite as clear there. But you have your 6 B's, and then you have the C's, which is where we might place some shellcode that we want to execute. Of course, we can't do that in this situation because the no execute flag is set, so we can't execute code on the stack. There are other things that we could do to potentially execute code, but this is an easy challenge. All we need to do is overwrite these B's with the address of the win function. So let's try and do that now. So we'll try to exploit this manually. First of all, let me create a flag.txt, and we'll just say flag fake flag. Save that just so we can see it printing out if we get it right. And we want to do this Python command again. We don't need to worry about these C's. What we want to do is replace these B's with the return address of that function that we want to jump to. If this was just a local problem, by the way, we could just probably say just jump to winner, and it would probably execute that. In fact, if we jump there, you see there it printed out congratulations. The issue is that obviously we need to do this on the server, and on the server we're not going to have access to GDB. We're not just going to be able to debug it and jump to wherever we want. So that wouldn't work in this case. But yeah, let's grab that address then. Let's do disassemble winner, and we can just get the address right here. We need to put it into little endian format. So let me go here. I'll paste it in here just so I can see what I'm doing, and we'll do \x06 because we're doing this in reverse order of the bytes. \x06 \x12 \x40, and we might need to pad it with some more zeros. I'm not too sure. Let's try this. If we print that, it's not going to print all the characters because this isn't recognized as ASCII characters. So let's print this to a file. We'll just call it payload, and then we can try and run our program again, and we'll send in the payload. And you'll see that we get here congratulations fake flag, and it returned our flag for us. So let's see if we can do this on the server, and then if we can get it working on the server, I'll also write a quick Pwntools script to automate this process for us and automate finding the instruction pointer and everything as well. So first we'll just do netcat, paste in that address and the port. Just make sure you remove that colon. We send that, it asks us for a name, let's say crypto, and we get the registered. Now if we do that again, this time we're going to send in that payload, And there you go, we've overflowed the buffer and we got our flag. So that's the server exploited. Let's see how we could have done this through the Pwntools library. What I'm going to do is I've got a Pwntools template that I'm going to use here. I'll put it here and call it reg.py. And let's open that up. Plug in whatever we need to. I'll just explain the template a little first. So there's a bit of code in here already. We import our Pwntools library. We need to set our exe name here. It's going to be reg. And at the start, it's going to identify what architecture, what bits, operating system stuff. It's going to find out that it's a Linux ELF 64-bit executable. We're going to not run checksec. We've already run that at the start, so you can have it run checksec here. Our context level set to info. This is handy to change this between info and debug, depending on if you're having any issues. We have a function here to identify the offset of the instruction pointer, and essentially this will try to crash the program. You can see actually in this case, this was a template that I used in the ROP Emporium challenge series. If you're interested in buffer overflow exploits, you can have a look at the playlist I put on the channel a little while ago. And so we might need to modify some of this. This is designed for a different input. I think we're going to need to say, what did it say there? It asked us for name, right? Enter your name. So what we're going to do here is we're going to copy this. Oh. It asked for the name, so we're going to paste this in here instead. And this is going to launch a new instance of the process, and after it asks for a name, it's going to send a cyclic pattern, in this case of 100, but we could increase this if we need to. It's going to wait for the program to crash, and then it's going to look at the core dump file, and we're going to say, can you find out where the EIP is? We're going to need to change this to RIP, because it's 64-bit here. And then it's going to return the offset of that. Once we found the instruction pointer, once we found the offset that we need, we can launch our process, or we can do a remote server if we're testing it against the server, and then we build up our payload. And our payload, we're just saying here, we flatten this into whatever architecture and stuff that we set up here, and at this offset, insert something. And in our case, we're going to say at this offset, we want to insert, where was this address? You can grab this address, you can paste this in here. It doesn't need all these zeros because it's already it's finding out that it's 64-bit here, so we don't actually need to worry about that. That's going to build the payload. Then we have some script here. It's not, if we have any problems, we can assign this so that whenever it sends the payload, we can debug it and see what's going wrong. So step through instructions line by line. And then finally, we send the actual payload that we generate. Again, we need to make sure that we have the right prompt in here. So we're looking for the enter your name. So let's paste this in here. And we're going to receive until thank you in that case. Let me see. In this case, we want to receive until congratulations. And then off whatever we get then, the next is going to be our flag, as you can see here. So hopefully, if we try to run this now, we're going to have some problems with this EIP. So let's just run it and see that happen. Let's do python reg.py. You see we get this error saying, hang on, the core file didn't have an EIP value. So we could go back here and actually say print out p.corefile.registers. Run that again, and you'll see it actually prints out all the registers and their values here. So we know there's no EIP because it's an RIP. So let's go back and give it the correct register name. Let's run it again, and we get an end of file error. Okay, so it didn't locate the offset there. 1 second. I think for the RIP we might need p.corefile.read, and then we'll say 4. I want to get 4 bytes. Oh, did I just accidentally? Okay, there we go. Let's try that. We get an argument that's missing. Count. Okay, so I've just put the 4 in the wrong place. Cyclic find. Let me put another. Wait, what am I doing? What am I doing? Right, okay. Let me go back. Let me go back and just take all that out. If you remember, the RIP won't be populated by the value. That's why we looked for the RSP value last time. Let's try that. Okay, we still get an error there as well. Alright, we might need to do the read as well as that. So, because the RIP won't load the invalid address, we'll need to give it the RSP value. Let's say p.corefile.read, and then we'll paste this in here, and then we're going to say 4, take 4 bytes. Let's try that. There we go. So it found the offset at 56 and it printed out our fake flag. Let me just demonstrate as well the setting this to debug mode. If we set the context level to debug, it'll give us a lot more information. So you can actually see as it's sending this off, what's it sending? It's sending a cyclic pattern here. Or actually that's the offset that it's sending. It's sending the offset for our 56 byte offset. You see right here the offset, and then this is the address. So it's doing that right there. Let me also demonstrate some other ways to do this. So we don't necessarily have to find the address of this because we're loading the elf here. This will actually that'll have all this information for us. Let me put this back to info. And let's say print elf dot functions. Let's run that again, and you'll see it's listed all the functions here and the address that those functions are at. So these are all actually available to us. So what we can do is just say at this offset, just go to elf.functions.winner. And if we run that, you'll see that we get our fake flag again as well. We can also, another thing we can do, if we want to save this payload, we can just say write, and it takes in, as you can see here, the path and then the data. So if we say, as a path, let's say payload. Let's say payload, and then the data is our payload. And if we, let me remove the payload we already have here, and let's run that again. Now if we print out the payload, you'll see that that's the payload. Rather than all the capital A's we had, it's the payload which has just been generated there. So what else should we look at here? Let's try this on the server as well. We haven't demonstrated this on the server. So let's grab our server address and port, paste this in here, grab the port number, and we'll send that off. And you'll see we get back our flag from the server. Another thing we can do, we could have made this a bit easier. Let me go back to our Pwntools script, and in here let's create a ROP object. We'll do ROP elf. See here, a class which simplifies the generation of ROP chains. So we generate that ROP, and let's do pretty print ROP.gadgets, and I'm going to put this back to local. I'll change this because I'll upload this script onto GitHub. I'll just anonymize those, and let's try and run that. You'll see here it gives a list of all the gadgets which are here. Name.io is not. Oh, we're missing the process bit there. Okay, so you can see it gives a list of all the gadgets. Something else we could do is use wropper. So you can do wropper and just pass in the binary. So wropper-f file, and we can get the gadgets this way, or we can do --search, and if we're looking for pop gadgets. None of this is needed at all for this challenge, but we'll look into that more on some of these Pwn challenges, and if you go back to the ROP Emporium series, you'll see a lot more of that sort of stuff. But anyway, let's see what else we can do here. We can also let's try, now that we have this ROP object, instead of even having to put in this function here, what we can do is just say ROP dot, and then we can pass in a function. So I'm going to say ROP.winner. If there were any parameters we needed to pass, we could actually pass the parameters in here as well. But in this case, I don't need to do that. So we do that. Let's put this a bit closer together. We do that, then let's say ROP.chain. Now we could go ahead and say, let's do info ROP chain, and then the ROP chain. Sorry, let me do ROP chain is equal to ROP.chain, and we'll print out the ROP chain here. And you can see here the ROP chain that it's created. Actually, let's do ROP dump. That will look a bit better there, I think. We'll do print ROP.dump. And yeah, there's not too much to look at here really. It's just calling the winner function, and it has the address. What can be pretty cool is if we were passing in like a lot of different parameters to winner, or it had to do some kind of, it had to assemble some different ROP gadgets to get to this winner function, then whenever we dump out that, we'll see the chain of gadgets that it had to chain together in order to execute whatever we're trying to do. In this case, there's not really much for it to check. But now that we have the ROP chain, or let's not even do the ROP chain there, what we can do is just say at the offset we just want to send the ROP dot chain. Now if we submit that, so we've done that instead of putting in the address there, and submit, and we get our flag back. So that's another way to do it. In this example, it doesn't make too much of a difference, but as we start looking at more stuff to do with ROP chaining, we'll see some better examples of this. Anyway, hope you've enjoyed this video. I'll put a couple of links in the description to some really good resources for doing buffer overflows and binary exploitation and stuff, and we'll move on to the next video.